Okay, we're going to get started. I hope you all had a good lunch and a good engagement with our students. I think that's always the heart of any academic conference, is just being able to directly talk to our students. I looked at the posters this morning when they were setting up, and they're fantastic. So we're going to kick off the afternoon with a keynote, which I think will be fascinating. So it's an honor to introduce our next speaker, Dr. Chris White. He is president of NEC Labs America. He holds a PhD in theoretical quantum chemistry from UC Berkeley and has spent his career bridging the gap between groundbreaking scientific discovery and market-ready technologies. Under his leadership, NEC Labs has become a central hub for innovations in computer vision, edge computing, and intelligent infrastructure, technologies that are obviously now the nervous system of smart cities, as we've been discussing today. He's a vocal advocate for building responsible, human-centered technologies and that solves meaningful problems at a global scale. And today he joins us to discuss the evolution of AI and what it means for the future of our connected world. So please join me in welcoming Dr. Chris White.
Thank you, and thanks again for inviting me. I always love giving these kinds of talks, and I'm going to apologize a little bit. I'm not going to tell you which stock to buy right now that's going to actually fund your children's education, but we'll, I think, have a fun discussion. And please do ask questions. I'm happy if you want to interrupt me if there's something that's really strong, but I'll try to keep some time at the end as well. So one thing just to start with, because I'm sure not all of you know NEC. NEC is a Japanese company. I didn't know anything about NEC before I joined either. They do kind of everything. There's not really a good analogy in the US anymore. They do satellites, they do digital health, digital finance, targeted cancer vaccines, they do smart cities, they do construction. It really is a sort of end-to-end just about everything. And what I run is NEC Labs America. So we're a lab that has 2 labs in the US, one in San Jose and one in Princeton, basically right next to the university. And we run NEC Labs, or I run NEC Labs, very much like Bell Labs. Right? So I was talking to Debasis Mitra of Columbia. He was my boss at Bell Labs. I was there for 23 years and basically got pulled to NEC about 6 years ago. And NEC Labs was started by someone from Bell Labs, and of the 7 presidents, 4 of them have been from Bell Labs. So our job is very much in that sort of vein of big disruptive research. So our goal is to take the problems that NEC has, which, as I said, touches all customers everywhere, and develop technologies looking at the state-of-the-art of where the space is, and couple that sort of state-of-the-art of academia into the business units, right? And our interactions with universities like Columbia are really because Columbia sits at the state-of-the-art, and that interaction is really what we love to do. My job is to sort of run the lab, but the fun piece is really to sort of think about the future and think about the research portfolio. So first, the apology, no one can see the future. That includes me. There's a longer version of this talk where I took some McKinsey estimates for what technology was going to be like in 2020 from 2010. Don't go back and look at that, because it's really not a happy projection. But one thing that you can do, and one trick that I often use, is framing the problem. So what I can do for you is tell you what the shape of the future of AI is going to be. And understanding that shape, you can understand the missing pieces, and hopefully that'll help you sort of guide and understand and be able to think about the space. What I'm not going to do is this. I don't know if anybody has seen this figure. It was really popular in 2023. When the hype of AI was growing really, really strong. What they did was say ChatGPT 2, GPT 3, GPT 4, let's draw a straight line into the future, and we're going to have, in 2028, advanced AI that can replace researchers and engineers. We're at the red dot right now. I'm not sure that, well, first of all, I'm not sure that a researcher and engineer is a million times smarter than a smart high school student. So that's one. But I'm also not sure that we're really getting close to that edge. But where these kinds of predictions come from are by analogy with this. So this is Moore's law over 1970 to 2020, and it draws an amazing line on an exponential plot. But the interesting thing here is, well, maybe I'll ask, does anybody know why Moore's law could continue? Any thoughts? Post-lunch thoughts? Quantum? Maybe not. Transistors in 1970 looked very much like transistors in 2020, except they were shrunk smaller and smaller and smaller and smaller, right? So there were very, very specific aspects of the speed and density of computing that translated directly into this overall speed. And therefore, we had one dimension to run along. And the thing that's important to think about this, the one thing that I will tell you that is absolutely true, is that what happens in life is entropy is always increasing, right? The second law of thermodynamics basically says that if you have a straight line like that it doesn't happen by accident, right? Nature doesn't evolve that way. You have to be putting an enormous amount of energy into that, and you have to feed that straight line in order for it to continue. So those in the audience that were around the sort of semiconductor revolution, there were industry organizations that sort of worked together to push that line to stay as straight as it could for as long as it did. In the case of AI, we don't actually have that one dimension, right? If we make the transistor smaller, then the power goes down, then the speed goes up. We don't have that kind of dimension in AI. And one of the things that I'm going to argue is that the AI of today is not going to turn into the AI of tomorrow by just changing one dimension. And that's why it's tricky, and that's what breaks a lot of those single plots that were out there. So first takeaway, trends need to be fed. You need to put an enormous amount of energy or enormous amount of money in order to keep these trends going for a long time. My suspicion, 2028, if you draw that real graph, you're going to see that it actually is turned over. And it's going to turn over, especially when the investment goes away, which sort of brings me to my sort of next piece, which is the best technology never wins, right? This is a very interesting chart we can have lots and lots of discussions about. But if you have a technology that is better than what the market needs, then it is too expensive by definition, right? You need to take something away from that because you're paying extra money to get quality that is above what the market needs. If it's below what the market needs, then you're also not going to win. It's the one that just hits at where the quality of the technology matches the needs or the expectations. And one of the things I would argue, and I will say NEC is making a large amount of money around AI applications, the AI we have today is good enough for many of the applications that most companies need. And the important piece is understanding the challenge of those companies. And if you can match those challenge with an understanding of not what AI is said to be able to do, but what it can actually do, you actually end up with very, very high quality applications that scale with the market. The interesting thing here, though, is, again, if you start looking at these sort of high-level pictures, if we actually plot the commercial value for the tasks that are necessary, or the tasks that people want to complete, you find that 20% of the tasks dominate most of the value of that commercial offering. And the same thing happened in the dot-com boom, right? So if you remember dot-com, everybody had an app and everything else. But the apps that actually made money, companies focused on developing those apps and they extracted an enormous amount of value for the 20%. So the AI that you're thinking that's going to solve every problem doesn't really exist. But AI that solves those 20%, That's what everybody's working on. And if you start looking at the announcements that are coming from current AI companies, it really is on optimizing for the 20%. And so the second takeaway that I'm going to have is that industry will continue to feed this AI monster that wants more and more money until those AI systems get good enough. And once they're good enough, maybe not AGI, maybe not ASI, then that money's going to disappear and you're going to see a pivot in the industry. And I would argue that that probably happened about 6 months ago. If you start watching, the Super Bowl commercials, I don't know if you've seen the Super Bowl commercials from Anthropic, but the second that AI companies start having Super Bowl commercials and they start fighting amongst themselves, you know that there's a pivot taking place. And that's an important thing for us to understand. So, does anybody know what this is? So I know there's some of you who have seen black and white TVs before. I know there are many of you that don't really understand anything about what's going on in this picture. I Love Lucy, yeah. I was going to say that, but I thought there might be a copyright issue, so I went with I Love AI. But the interesting thing about this is that when black and white TV was all there was, everybody thought it was wonderful. Nobody was sitting around saying, oh, I need a color TV now, that would change everything. And they didn't take the black and white TV and just make it better, right? It wasn't a linear connection of making better and better black and white TVs until it turned color. It was really that realization, that disruption that added a feature, right? So the thing to think about here is they added an adjective to TV, right? They didn't say black and white TV, they just said TV, and then magically there were two kinds of TV. And that was a big, big disruption in that space. And I would argue that you're going to see the same thing in the AI space. This is an interesting plot, and timeline. It basically shows the major machine learning technology as a function of time. And you'll see that it runs in 10-year cycles, right? So 10 years for expert systems, 10 years for SVMs. A little bit, you could probably change the naming. But transformers, which are the base of modern AI systems, large language models and everything else, it's had its 9 years. And that means that the next big thing is probably either published last year at NeurIPS, this year at NeurIPS, and you're going to see that transition take place. And the transition's not going to be bigger large language models. We already learned that doesn't get us to reasoning, which is what the world wants. It's going to be some new adjective that we're adding into this machine learning space to actually build something differently. And if you see, and if I have time in the talk, it's going to probably be around representation or prediction. That's where the world is really going. So takeaway number 3, evolution will be discrete. It's not going to be a continuous evolution getting better and better and better. Even though the investors want that, even though the companies that have it want that, it is going to be some kind of discrete change. Now here I am going to need a little audience participation. So this is a bunch of polyhedral die. If I said, I will give you $1,000, you pick the die, you pick the number. If you roll the die and you get the number, then I'll give you $1,000. What die would you pick? Sorry? 4, yeah. Right, it's kind of obvious. You want to pick the die that has the smallest number of possible outcomes, right? And this is related to a whole bunch of different things. But again, DeBossis will be happy with me now with this. So this paper by Claude Shannon, if you haven't read it, you should. If you read this section, you'll find out that he's talking about basically large language models in one way or another. But the critical piece of this paper was that he actually took communication, which was, quite frankly, in the same model as we have today, right? There were people selling faster than light communication and underwater communication and all sorts of things. And what Claude Shannon did was focus the entire industry and gave them a direction for the best they could possibly do inside of communication for a channel. And the same ideas of entropy and surprise and everything else you'll see in this paper are built into what the next evolution of AI systems is going to do. Large language models have done an amazing job of being able to predict the next character, of being able to predict answers to a question. But if you start looking at it, things like hallucination aren't because the model is making an error. It's built into the nature of what they're doing, which is directly related to these kinds of entropic ideas. Right? If you allow a model to answer, anything that it wants, versus if you give it constraints, the anything it wants means that it will. It will explore the space and it will give you something, and that's really what hallucination is. So again, just in the thoughts that I'm trying to inject, entropy will be important, right? Specifically, the theoretical understanding of these AI systems is going to be a critical thing, right? I often show that slide, and I say, there's a child like this that's going to write a paper like that basically makes all of these data centers not necessary anymore, right? I'll sort of give the conversation that my parents didn't spend $2 trillion in training me to speak English. I suspect it's the same for most of you. So the idea that we have to do that as a society, right, $500 billion data centers is kind of silly. And the reason why we're doing that is because we don't understand the mathematical underlying piece of this. And that is the analogy to what happened with Shannon. So that's coming. So let's talk a little bit about what we're doing now, though, right? I said that's sort of the future, but right now is kind of okay. So I'm going to talk about three different things. I'm going to talk about knowing things, I'm going to talk about doing things, and I'm going to talk about predicting things. And if you think about it, there's three different kinds of intelligence there, right? It's knowing things, being book read. There's doing things, being able to be, a blacksmith, or 10,000 hours of time to become an expert. And then there's predicting things like knowing that if someone has a fever and they have a rash, that they probably have a certain kind of disease. Now, the interesting thing about this is that knowing intelligence, we have lots of data. Somehow we managed to get everybody in the world to spend 30 years creating lots of data that enabled the AI that we have today. On the doing intelligence, maybe we have computer programs, but if you see, it's basically 9 orders of magnitude lower. But we have almost nothing with respect to inspecting intelligence. So it is very, very clear that even though we think, wow, we have all this great AI, we've completely neglected two kinds of intelligence. And so the kind of AI that we see, right, the new characteristic that we add, the new adjective we add to the name, might be landing in one of these spaces. And let me show you one area that might be possible. So there's a model that was put out by it was actually a Japanese professor, about the way knowledge moves inside of organizations, right? And he basically talks about this sort of tacit knowledge that exists inside people's heads and explicit knowledge which is sort of written down. And there's a path where, people talk to each other to actually explain ideas. People write manuals that translates information from being tacit to being explicit. So if we look at this diagram, in the sort of modern AI world, all of the AI we've been doing is over in that lower right-hand corner, right? We're taking explicit knowledge, stuff that was written down, and we're actually training models to actually create this AI knowledge, and then inference is really generating data from that, which actually makes it explicit again. But in the upper left-hand corner, where we have tacit knowledge inside people's heads, that has gone completely untapped. And most of what we need to build as an industrial partner to companies is understand their tacit knowledge, understand what their key engineers know, and build AI systems that actually replicate that kind of behavior. So this idea of tacit knowledge and how we can extract it, how we can use it for learning, is a critical model. So next takeaway is that we've already, unfortunately, done the easy intelligence, right? It may think, super hard, and it certainly took us a long time to get there. But all the raw material, all the data was there already. And now we need to figure out how to do these other areas where the data doesn't really exist. So let me jump through a couple other things quickly and sort of show you another direction. So one is the enterprise tacit knowledge. The other is the sort of real-world applications we build. So we have to deal with complexity. We have to deal with scale. And not just scale, doing it for a large number of people, making it individualized for every person across the entire planet. And we have to do it with low resources. So how do we do that? What does it look like? Well, what it looks like is something that looks like this, right? We've always lived in the real world in real time, right? If you trip and fall, you hit the ground, there's nothing you can do about it. In the last maybe 5-10 years, we've gotten the ability to interact with the digital world in near real time as well, right? No one actually worries if their cell phone is connected anymore. They assume that it's going to be. So we've really transitioned there. And the next phase is really this idea of actually building digital representations of the real world that are real-time accurate, right? Which fits very much with the center, the kinds of things that I saw on the posters and everything else. This is a critical path that we need to go through. And then if we look at that and we sort of unfold it, then we actually get this kind of very interesting idea where we sense in the real world and we sort of cross this blue line into a digital space where we have to perceive the data, right? We have to, we as human beings are constantly inundated with huge amounts of information. Our brain learns how to ignore most of the things except the things that are most critical for what's going on next, right? We sort of extract the features. We then try to understand if those features have repeated before. And then based upon what's going on, we make a prediction and then cross the blue line back in the real world to take action. And the key is, between these two blue lines, that has to happen in near real time. So how do we actually build this sequence? And you'll notice that the key pieces, perception, understanding, and prediction, are where AI should be doing lots of the heavy lifting, right? So when we start talking about robotics, right, we do have lots of good sensors, but the key is how we actually manage these interior pieces. And the last thing I will sort of leave you with is that where you're going to see the next evolution is going to be on these two pieces. How we actually represent data, right? And I have a whole bunch of slides in another talk we can talk about, but the key to solving a problem is understanding the notation for being able to write down the answer, right? Think about that for a little bit, right? If you don't know the notation, or if you can't write down the problem, then you can never write down the answer. And if I pick the right representation, then the answer to a problem is trivial. So the whole idea of AI right now is building this representation that's internal to the AI system. We don't know what it is. We have to understand that better, and we have to be able to transform between different representations in order to understand what's going on in the world. And then once we have that representation, we have to learn how to predict what's happening next. And it's not just a 1D token prediction. It's is this person going to walk off the sidewalk into the roadway prediction? So it is a multimodal, many dimensional prediction. And therefore, the representation that we pick, we want to be optimized for the kinds of predictions that we actually want to make. So I'll leave this with my sort of last takeaway, that the key, if you want to focus on where this is going, is look at representation and look at prediction. Those are the key attributes that are, one, if we find the right representation, we dramatically reduce the size of these models, and we allow for computation on edge devices and everything else that goes in. And to understand the prediction piece, we really need to do more than just look at patterns. We have to look at physics. We need to do machine-inspired machine learning and try and understand how we can actually, with very small amounts of data, make these large predictions. So that's my talk for now. I see there's 2 minutes on the clock, so hopefully we can have a question or two. Thanks. While you're coming down, I'm going to do one more slide. Take a guess, what is the next word? Blue. Falling, blue, okay. Pretty easy. What are the next 7 digits? So, obviously, both of these are the sky is, but this is a binary representation of the sky is. The first one, your brain is super good at predicting the next word. This one, not so much. So that's the idea. If you have a good good representation, it is really easy to predict the next thing. A bad representation, nothing you can do.
Yeah, phenomenal talk. Thank you for doing that. I'm just curious, out of all the hyperscalers out there, right, developing the huge LLMs and the smaller versions, you know, the Chinese, the DeepSeek, where do you see the much smaller consumer-focused LLMs, right, for very specific tasks? Where do you see that playing out?
Yeah, so this gets a little bit in the investing thing, and I don't know if you've seen the Super Bowl commercials, but you should watch those. We are going through a pivot right now where all the companies that were sort of creating God models, right, a model that could solve every problem, they realize, oh, every time we've tried to do that in the past, it never worked. So now they're trying to pivot. So Claude, for example, just released a model specifically for legal. Right? Claude, many of you probably know, is really, really good for coding. So what I suspect you will see is a split. All of these different companies will lose this idea that they're going to try and build a model that solves everything and start creating the individual applications. Right? The real trick of all this from a money-making standpoint is companies can't consume LLMs. That's why there's no money coming in, and that's why all the pivots are taking place right now. But if you actually understand a corporate challenge, then you can use an LLM as a tool to actually solve that piece. So the money from LLMs is not something new. It is how you make your current product better, and in making your current product better, you can actually make a lot of money. So I don't know if that helped answering the question. I think there's going to be a lot of pain for all of them. I'll give you my one other bubble prediction. I think the investment markets are going to move wholesale into robotics, right? Because robotics is another thing that they can say, if we solve this problem, it makes everybody's life great. And everybody is tired of AI right now because it didn't make their life great. And they want to think that robots will. And that means the bubble money that's around AI right now is going to flow into be bubble money into robotics. So if you're looking for academic funding, world models, you know, all of that, that's going to be a big, big deal. Yeah, it's a super hard thing. I will tell you, I have a son who's a junior at Purdue, computer science and economics, and he's asking me, Dad, what am I going to do? I'm never going to get a job. What's going to happen? I think the thing that happens is that, well, I'll tell you what we look for when we hire, right? I want to find students who know something deep, right? So they understand it right to the, you know, the tips of their toes. But they also understand how to actually look at a new problem and translate that problem into the area that they know deep. Could be mathematics, could be computer science, could be whatever you want, and then solve that problem in their own representation and then convert the answer back out to the person who's asking. So that argues that students should have some depth. You should have something where you say, I am an expert at X. And I wouldn't say if you're an expert at OpenAI or if you're an expert in PyTorch, that's probably not something that's going to be here 50 years from now. But if you can say, I'm an expert in mathematics or linear algebra or discrete math or computer science or algorithms or biology, or I'm a chemist, by the way, that stands the test of time for depth. And there's a lot of stuff to learn. And then the next piece is you need to understand and get experience in lots of different places, because that allows you to take your understanding and turn it into understanding in another space, right? That is the key. If you build yourself as a technical problem solver with depth, that will get you a job, right? I used to talk to high school students a lot, and I would say, how do you make money? And they would say, you be a rapper. I said, yes, you can make money as a rapper, but the way you make money is to be able to do something that nobody else can do. So if you're a computer science student and you're just learning what everybody else is learning, you're going to have a hard time because there's a big pool of computer science kids to pick from. But if you can actually say, well, I worked and I pitched a startup in an entrepreneurial boot camp, or I worked on this or worked on that, all of those things are ways that you differentiate yourself from the mean, and that is what employers want to see, right? They want to see where you have distinguished yourself and solved the problem in a way that makes you unique from all the other people that are coming in.
Thank you very much. Please join me in thanking Chris. Thank you very much. That was a fantastic talk and reassuring to see that we're doing the right things, I think, at CS3 as well. So that's validating. So next up, we're going to one of our, the second perfect pitch competition session, short session. And I'm going to welcome up, actually it was the winner of our accelerator competition 2 years ago, Mashid Gassemi. She's going to MC this session, and yeah, so welcome